right, today we are tackling an absolute legend in the world of physics. I'm talking about the problem book by I.E. Irodov. Now, if you've ever studied physics seriously, that name probably makes you, well, it probably makes you feel something. We're talking about some of the most challenging, but also some of the most satisfying problems you'll ever come across. And listen, this book doesn't pull any punches. It tells you right up front what it's all about. This quote is from the preface, and it basically says, hey, this is for people doing an advanced course in physics. It's famous for being really, really rigorous. This isn't about just plugging numbers into a formula you memorized. Irodov forces you to think from the ground up, from the fundamental principles. So, what are we going to do today? Well, that brings us to our challenge. We're going to pick one of these classic problems and we're going to solve it together, step by step. You can think of it as a fun workout for your physics brain. Let's see if we can crack it. All right, let's get into it. The Irodov Challenge, problem 1.11. This one is from the very first chapter on kinematics, and it's a perfect example of an Irodov problem. It looks kind of tricky on the surface, but once you find the key, it just unfolds so nicely. Okay, let's read this out. Two particles move in a uniform gravitational field with an acceleration g. At the initial moment, the particles were located at one point and moved with velocities v1 equals 3.0 meters per second and v2 equals 4.0 meters per second horizontally in opposite directions. Find the distance between the particles at the moment when their velocity vectors become mutually perpendicular. Phew. Okay, so what's really going on here? We've got two particles, right? They start at the same spot. One gets shot to the right, one gets shot to the left. At the same time, gravity starts pulling them straight down. Our mission is to figure out how far apart they are at the exact moment their velocity vectors become perpendicular to each other. Okay, first things first, with any problem like this, we need to decode what's actually being asked. Let's translate all those words into physics we can work with. This table is perfect for cutting through the clutter. Let's just lay out everything we know. For particle 1, we'll say its initial velocity in the x direction is positive 3. For particle 2, since it's going the opposite way, it's negative 4. And what about the y direction? Well, they're shot horizontally, so their initial vertical velocity is just 0 for both of them. And the acceleration? That's just gravity, pulling them down. So we'll call that negative g for both. Simple as that. So just to be super clear on our goal here, we need to find the distance, let's call it L, at a very, very specific moment in time. Not just any time, but the one single instant when their velocity vectors v1 of t and v2 of t form a perfect 90-degree angle. That's the key. All right, so how do we even begin to find that moment? Well, we need to get our toolkit ready. And since this is a classic kinematics problem, things moving with constant acceleration, we can reach for some of our favorite, most fundamental equations. And here they are. These two vector equations are going to be our best friends for this problem. They're the workhorses of kinematics. The first one lets us find the velocity at any time t, and the second one tells us the position at that same time t. With just these two, we can map out the entire flight path of both our particles. Powerful stuff. Okay, this next part, this is the real heart of the problem. That little phrase in the problem statement, mutually perpendicular, that's not just flavor text, it's not just a description, it's a direct mathematical instruction. Honestly, it's the key that's going to unlock this whole thing. This is the aha moment. So I've got a question for you. How do we do that? How do we take that word perpendicular and turn it into math, like an actual equation we can solve? What's the mathematical test for two vectors being at a right angle? The answer? It's the dot product. This is the perfect tool for the job. You might remember this from your math classes. It's a way you can multiply two vectors, and the result isn't another vector, it's just a single number, a scalar. And here's the magic trick. If that number comes out to be 0, then the two vectors are perpendicular. It's an incredibly clean, powerful test. And just like that, everything changes. What seemed like a messy physics problem about particles flying around has now become a really focused math problem. All we have to do is find the one time, t, where the dot product of v1 and v2 equals 0. That's it. Once we find that t, the rest of the problem is going to be a walk in the park. So now that we've had our big aha moment, we can actually lay out a battle plan. We know the strategy, now it's just a matter of executing the steps. And here's our roadmap. It's a simple 5-step plan. First, we'll write down the full vector equations for the velocities. Second, we'll calculate their dot product. Third, we set that dot product to 0 and solve for our magic time t. Fourth, we'll use that t to figure out exactly where each particle is. And finally, step 5, we calculate the distance between them. See? Nice and logical. Okay, step 1. Let's write out those velocity vectors. We just use our v of t equals v0 plus at equation. For particle 1, the x component, the I hat direction, is just a constant 3. The y component, the j hat, starts at 0, and then gravity adds a negative gt. Easy enough. For particle 2, it's almost the same. The x component is negative 4, and the y component is also just negative gt. Done. All right, steps 2 and 3, let's do the dot product and solve for t. Remember how it works? We multiply the x components together, so that's 3 times negative 4, which gives us negative 12. Then we multiply the y components together, that's negative t times negative t, which is a positive g squared times t squared. We add those up and set the whole thing to 0. A little bit of algebra, move the 12 over, and boom, we find that t is the square root of 12 all divided by g. That's our special moment in time. Step 4. Now that we have our time t, we can figure out exactly where these particles are. We just plug t into our position equation. For particle 1, its position is its initial x velocity, 3, times t in the I hat direction. And its vertical position is that negative 1/2 gt squared term. For particle 2, same deal. Its x position is negative 4 times t, and its vertical position is, wait a minute, it's also negative 1/2 gt squared. See that? Their vertical drop is exactly the same. That's going to be important. And now for the final step of the calculation, step 5. To find the distance between them, you just take the difference of their position vectors, so we subtract r2 from r1. And here's where it gets really cool. Remember how those vertical j-hat components were identical? Well, when you subtract them, they cancel out. They completely disappear. The distance between them is just the horizontal distance. So we have 3t minus a negative 4t, which is just 7t. How clean is that?
Okay, we are on the home stretch. We know the distance is 7t, and we know what t is. Let's put it all together and get the grand finale.
Now, just for fun, if you check the back of the Irodov book, you'll see this general formula for the answer. It looks a little scary, right? But let's check our work against it. The v1 plus v2 part, well, that's just our 3 plus 4, which is 7. And the square root of v1 times v2, that's the square root of 3 times 4, which is the square root of 12. So the whole formula is just 7 times the square root of 12 all over g. That is exactly what we got from our 7t. Perfect. Our logic holds up. And now for the number itself. We just plug in the value for g, which is about 9.8 meters per second squared. We do the math, and we get about 2.5 meters. There it is. That's the answer to Irodov problem 1.11. So think about what we just did. This problem, which looked pretty complicated, didn't need any crazy calculus or pages and pages of algebra, did it? The whole solution hinged on one single insight. It was all about recognizing that the word perpendicular was a signpost pointing straight to a mathematical tool, the dot product. And once we had that key, the whole thing just fell into place. It's a great reminder that with physics problems, sometimes the trick isn't being a human calculator, it's just finding the right way to look at the puzzle. What other tough problems out there are just waiting for the right perspective to unlock them? Thanks for taking on the challenge with me.